So previously we got our difference equations for the sine wave using a continuous system, and then we transform this continuous, this Laplace domain, to the z domain, into this digital domain using the bilinear transform. But now we are going to use the z transform, and we will start purely already digital. So we have this sine function. This is n is the samples, and t is the sampling period. So if we consider the sine function, and we can have the unilateral z transform for this sine function given by this definition here, the sum going n going from 0 to infinity. We have the z to the power of minus n here. Again, if we will recall the Euler identity for the sine, we can express the sine as these two exponentials. Then if we apply this, so we replace the sine by this, and it makes easier for us to calculate, and we have this z transform, and then we can rearrange so that we have these parts here. So this goes out of the sum, and we have one exponential. We have this z to the power of minus 1 times n, and here the same. Using this geometric series, we get this result here in terms of z to the power of minus 1, here in terms of z. And we can continue doing some manipulations. So here, now we will take this common denominator here, then we will get this. So this is common denominator. We have z times z to here, and minus z times this, and we have here. So now we can also multiply here under, so the denominator, we will get this. We also multiply the denominator, and we'll get this. Now we can put z here in evidence, and then we will have this z squared cancels with this z squared, and we will end up with this. Here we have z squared plus 1 here, and then we can put this z in evidence, and then we will get this. And now, looking again at the Euler formula, we already see that we have a sine here. So if we recall the Euler formula, so we have here, and this is here, the appears. And also we have, if we just this part here, if we divide and multiply by 2, just so we can have this here is a cosine as well. This is the Euler's formula for the cosine, and then we will end up with z times the sine. So the sine goes from the Euler formula of this divided by this, and here we'll have is z squared plus 2 times z times the cosine. So we have 2 times z here, and this is the cosine, so it's here, plus 1. And we can also have, this is in terms of z, and here we can see in terms of z minus 1. Now, if we will consider the following z transform to be a transfer function, and then we would have an impulse as an input to our system. Here we have our transfer function for the sine wave that we've seen. So if we want that when we apply an impulse, there we have this system that we calculate previously, then this should be a sine, the output should be a sine. So we can go from the z transform to a difference equation. So we will apply the inverse z transform, and we have here our transfer function. We cross multiply like we did before. Z to the power of minus 1 in this case will become x of n minus 1. Z to the power of minus 1 in the denominator will become y of n minus 1, and this is y of n minus 2. So again, we have these difference equations, and we want to have 0 initial conditions. So y of 0 is equal to y of minus 1, that is equal to y of minus 2, that they are all 0. And we know that our impulse it's 1 when n is equal to 0 and 0 elsewhere. So we can do again what we did previously. So when n is equal to 0 in this equation here, so x of minus 1 is 0, so this part disappears, and we will have this is 0, this is 0, so everything is 0, so y of 0 is 0. Now when n is equal to 1, if n is equal to 1, x of 0 is 1, so we have the sign that it's here, and also we have that this is 0 and this is 0, so this cosine part disappears, so we will end up that y of 1 is the sign. And then when n is equal to 2 or more, then we will have all the x when n is 1 will be, or here it will only be 1 when x of 0, that means that n is equal to 1. So for all other values this disappears, so we don't have the sign, and we will keep with this, because now when n is equal to 2, then it's y of 0. Y of 0 is 0, but y of 1 is given by the sign. And when we continue, when n is equal to 3, and then we will get this recursive relation. So we will implement the same style like we did before. So we have our difference equations, we have our y of 0 and y of 1, and in this example, instead of generating a 500 Hertz, we will generate a 1000 Hertz. So we have the same sampling frequency, and now we have these two coefficients we need to calculate. So I'm calling this coefficient A, which is the 2 times the cosine of 2 omega t, which appears here. And also we need to know the n y of 1, that is equal to the sine of omega t. So y of n1 is the sine of 2 pi ft. So now we are defining a buffer. So we'll have our y of 0, our y of 1, and our y of 2. Then what we'll do is in this loop, the output gets this buffer at position 0, so it's the y of 0 times our amplitude, and then buffer 0 gets the value of buffer 1, so y0 becomes y1, y1 becomes y2, so it's kind of a shifting this to the left. So this goes here, and then we will calculate the new number, and it will go here, and all the time we will return this to the output. So we are returning y0, but we already have y1 and y2, and this is how we generate now 1000 Hertz. The amplitude is 1000, peak amplitude from peak to peak is 2000, and we also can listen. So once we have our difference equations, we are doing the same principle. We're defining some coefficients, but this time we're just using this buffer instead of defining here as we did previously. We use these static floats inside this main, but now we will use a different principle when we implement in C for our processor.